Okay, so let's get going with our next lecture. We've been working on force vibration in the last couple of lectures, and so this carries on with force vibration. What we're going to look at this time is there's a couple of important other cases that are different from the previous case we looked at. So we're going to look at what's called a support motion and also a rotating mass excitation to our single degree of freedom system. Okay, so as I say, two cases we're going to look at. The first is called either base motion or sometimes it's called support motion. And what that means is we have our single degree of freedom system just as we have previously with our mass, our spring, and our damper, like this. So K for the spring and C for the damper. But in this case, we're going to shake the thing that the whole system is on. So we're going to move this base plate, if you like, with a signal y of t, and then our mass will move with a displacement x of t, just like it did previously. Okay, so this is important so for example, automotive engineering is a classic case of this, where this type of representation is what they call a quarter car model, or a quarter car body model. Okay, so you take a quarter of the car's mass, you assume that the spring and the damper are the suspension system, okay, and then you assume that there's an input from the road coming up from below, which is y of t, so like a road input. So it also has relevance for things like aircraft when they're taxiing and so on. Or if we have subsystems in an aircraft, so for example, if we've got like a system in an aircraft and it's experiencing some input from a support that it's mounted on, then this is the case that we'd have to analyze. So if we do the free body diagram of the mass in a way that similar to what we've done before, then again, if we take this assumption that we're trying to move the mass upwards, then initially the inertia wants to resist that and stay in its position where it is, and then we've got a restoring force trying to drag it back down as well, which is the spring constant x minus y. Okay, so the difference now is that the spring depends on the position of y and x. Okay, so in the previous examples, the bottom was clamped and we just moved the top of the spring, so the spring force was k times x. But now the bottom and the top of the spring can move, so it's like the relative displacement, okay, which we multiply by k to get the spring force. And it's the same with the damper force. We have a relative velocity now, x dot minus y dot, okay, and we multiply that by our constant c to get the damper force. So that gives us an equation of motion for this system, which looks like this. Well, the inertia term is the same as before, but now our damping term and our stiffness term have this new format. So we write down the equation like this. And if you remember in previous lectures, I've said that terms on the left-hand side relate to the mass and the spring and the damper, and on the right-hand side they relate to the forcing. Okay? So in this case, we've kind of got a choice. We can either leave the equation like that, or we can expand out the brackets and take the y terms to the right-hand side, okay, so that we're clear that that's what's forcing the system. Okay, so if we do that, what we get is mx double dot plus cx dot plus kx on the left-hand side and we get ky plus ky dot on the right hand side, so that's a y dot there. Sorry, that should be c times y dot, shouldn't it? So this format is nice in the sense that on the left-hand side now, the equation is exactly the same as it was before for the previous cases. And on the right-hand side, we're clear that the y signal is the forcing, if you like, by moving the base of this thing that the oscillator is sitting on, we are clearly denoting that it's the y signal that's giving that force. So if we assume harmonic motion, so just like we've done for all the previous cases before, we can express our system like this. So what I've done is I've assumed that x is equal to big X e to the j omega t, and that y is equal to big Y e to the j omega t. Okay. Now, if you wanted to, you could include a phase difference if you wanted to. Which I think we've done in previous lectures, haven't we? So in previous lectures we've looked at the phase difference. I'm not going to do that again, okay, but just to note, if we wanted to, if we thought the physics matched with a phase difference, we could include it, okay? But for now, what I'll do is I'll look at this expression. Okay, we can divide out the e to the j omega t's, can't we? And we can get big X over big Y is equal to k plus j omega c over k minus omega squared m plus j omega c. And this is called the transmissibility. Which has got a lot of I's in it, I think, transmissibility. And I'm an engineer, so I'm not very good at spelling. Okay, so I think that's the right spelling. But if you're like me and you're not very good at spelling because you're a natural engineer, then what you do is you just keep chucking I's in until you get to a Y, and then you say that's good enough. Okay, so that's my policy on words like transmissibility, just, you know, a consonant and then I and then something, keep going. When you feel you had enough, stick a Y on the end and you're done. So we can, if we divide top and bottom by k, so this is on the right hand side now, what you'll see is we've got expressions there which we've dealt with before. Even on the top, the expressions on the top are just two of the expressions which we had on the bottom. The bottom expressions, we've dealt with them all before. Okay, so in the previous lectures we had these expressions and we divided k out and made it simpler. Okay, so if we do that again, what we get is x over y is equal to 1 plus j 2 zeta r, and that's all over 1 minus r squared plus j 2 zeta r. So if you want to know where the 2 zeta r comes from, we derived that in previous lectures. So we derived that j omega c divided by k could be written as j 2 zeta r. Okay, so that should be all in the previous notes. And what we normally do is take the modulus of this. So we normally are interested in this relationship, and it turns out for functions of this type, that's essentially what we do is we take the square root of the square of the real and imaginary parts, okay? And it turns out for this expression that that's relatively simple. It's just this. Okay, so last time we did about frequency response functions and dynamic magnification factors, didn't we? And we were interested in the size of the amplitude of response as the frequency ratio varied. It turns out for this case, when we draw the graph in a minute, we'll see that when x over y is equal to 1, is an important point, and we'll explain why in a moment. When we draw the diagram, you'll see why. But what we do first, we're going to set x over y equal to 1 and work out what r values that relates to. So we have this relationship here from the square root function. Okay, so we can square both sides, can't we? And then multiply through. So if we square both sides and multiply through, what we get is something like this. So I can subtract 2 zeta r squared from both sides, can't I? So that means that I have 1 minus r squared all squared equals 1, which I can expand out to get r to the 4 minus 2r squared plus 1 equals 1. And so I've got 1 on both sides, which I can get rid of, and so actually what I've got is r to the 4 equals 2r squared. And so r equals 0 is a solution. And then, of course, I can divide both sides by r squared, so that I get the second solution is related to r squared equals 2. So r equals the square root of 2. And we know that r is the ratio of omega over omega n. So omega is equal to the square root of 2 times omega n for this special point where the transmissibility is equal to 1. Okay, so this is all just for the special point where transmissibility is 1. And in fact, this point is called the crossover frequency. So this value here, when omega, the forcing frequency, is equal to square root of 2 times omega n, the natural frequency, that's called the crossover. So let's draw a sketch of what this looks like. So what we're going to do is we're going to draw the transmissibility, which is the modulus of x over y, against the frequency ratio r. And what we've worked out is that when r equals 0, x over y is equal to 1, isn't it? Okay? And x over y equals 1 is an important point, because if you think about it, if you're putting in a signal at y and then x comes out bigger than it, then x over y is going to be greater than 1. Okay, so you're going to get a bigger response out than you're putting in. If x over y is less than 1, then you're reducing the signal. Okay? So what you find happens with transmissibility is that you go from 1 up to a resonance, and then you go back down again, and then at this point here you cross over. So this is the crossover frequency where omega is equal to square root of 2 omega n. Okay, so these are the two solutions for the transmissibility being equal to 1. R equals 0 on the left hand side, and then R equals root 2. Okay, so this is R equals square root of 2 here, isn't it? Or omega equals root 2 omega n. So on this, to the left of the crossover frequency, what's happening is we're amplifying. Okay, so we put a signal y in to the base, and what comes out, x, is bigger. Okay, so that's usually what we don't want. Normally we want to reduce vibrations. So if we can operate on the other side of the crossover frequency, here we're attenuating. Or reduce, it means reducing, right? Attenuating means reducing, amplifying means increasing. So if you're trying to design a vibration system, or a system that has mass and stiffness, and you want to work out where you should put your frequencies, where you should design your parameters to operate, if you operate above the crossover frequency, then any signal you put in, you will actually reduce. Okay, so you'll come out lower. The thing to notice is that with this, is that if you increase the damping, something a bit strange happens. Okay, so if I increase the damping, this resonant peak will go down, just like we did last lecture. We looked at the resonant peaks. Okay, so what happens is, if we increase the damping, we get a smaller resonant peak like this. But all the curves go through the crossover frequency, and on the other side, what happens is that this curve goes up higher. Okay, so it's a bit like as you push this thing down on the left, the thing on the right is trying to go up. Okay, because sometimes engineers think, well, I'll just add more damping, and that will help me. And if you're on the left, it does help you, but if you're on the right of the crossover frequency, it makes things worse. Okay? So you need to be careful. So let's say this is adding damping. Which what does that mean? It means making C bigger. Okay, so when I say adding damping, what I mean is that coefficient C that we had in the original equation, if you make that bigger, that's effectively adding damping, isn't it? So these kinds of vibrations are interesting, particularly for aerospace engineering, from when you've got cabin vibrations happening from engines, either in helicopters or fixed wing aircraft or whatever. This is all coming as a kind of support input, if you like. The fuselage or the cabin is being excited by something which is basically attached to it and is shaking it. It's acting like a source of vibration. So this kind of transmissibility design is quite important. So the second type of forcing we're going to look at today is forcing from a rotating mass. So okay, so in this scenario, what does it look like? Okay, so what we have is we have our mass as normal. Okay, but I'm going to write m in the top left-hand corner this time to leave some room for some other things. Because what we're going to assume is that we've got another mass here, which is we're going to call big M. Okay, so capital M is this other little circular mass. And that circular mass is rotating around in a circle, like that. Okay. And then we've got a spring, as normal. K, and a damper, dashpot, C, like that. In this case, the base is clamped. Okay, so the bottom is on solid ground now, we're assuming. So there's a couple of other details to think about. If we think about what's happening on this rotating mass, which is calling capital M. Okay, so it's rotating with an angle omega t, which means it's going round and round and round at frequency omega. Okay, and omega t makes this angle, if you like. We're going to call the length here E, small e. And there's this kind of history to why it's called E. It's because it stands for eccentricity. Because very often these types of problems come from what are called unbalanced mass problems. Okay, so if you have a high-speed rotating component, like a gas turbine engine or a helicopter rotor, if you've got a very, very small eccentric distribution of mass, so if the mass is not perfectly symmetric, which in nearly all cases is very difficult to manufacture things to be perfectly eccentric, then in effect what you have is it's equivalent to a small piece of mass rotating around at high speed. You have the same things in cars. So when you go to get your tyres fixed at a tyre shop, they balance your wheels. Okay, and what they're doing is they're trying to eliminate the irregularities in mass distribution in the wheel. Sorry. So what you do is you assume it's the center of the mass. So from the pivot to the center of the mass, which is what I've tried to draw it sort of. So when you've got things like lumped masses, we're always working from the center of the mass or the effective center. Okay, so if it's an irregular shape, then we'd work out from the effective center, if you like. Okay, so that's why it's normally called E. It's like for the eccentricity. And of course, what happens is that there's an interaction between the pivot point of this small mass rotating around and the big mass, isn't there? So we're going to have a vertical force Fv and a horizontal force Fh. And so strictly speaking, on this first diagram, what we need to do is we need to kind of show that this is constrained. Okay, so this mass here is somehow constrained, so it can't move horizontally. Okay, so it's still, we're going to still assume that it can only move vertically. Okay, so it can only move as usual with our x of t type of coordinate. But those little rollers and the wall are there to signify that it can't move in the horizontal direction, despite the fact that this rotating mass will create a force in that direction, won't it? Okay? So, let's draw the free body diagram for the large mass. So in fact, what's happening now is that this mass, if we take the other piece away, we're going to write this as m minus big M, okay? Because in the original problem, its total mass, the total mass of the two together is m plus, well, we'll call it m, all right? So that's the total mass. So this is the mass of the bit without the rotating component. And there's a pivot point here, and of course there's equal and opposite reaction forces on this pivot point, aren't there? And because it's a free body diagram, we have exactly the same other forces acting on it. So there's an inertial force when we initially try and move it. So in that case it's m, small m minus big M x double dot. And then we've got kx as a restoring spring force and c x dot as the restoring damper force. So, in the vertical direction, we've got m minus big M x double dot plus fv plus kx plus cx dot equals 0. Okay, so that's just taking vertical equilibrium of the big part of this mass here. Then from the rotating component we can work out what Fv is using force is mass times acceleration. So Fv is the big mass times the acceleration. So the acceleration is the second derivative with respect to time of the motion. Okay, and the motion is going to be x, okay, because the pivot point is going to move up and down with x. And then it's going to be this part of the motion here, isn't it? This vertical component here. Okay, so that's going to be E multiplied by sine of omega t to get that vertical component there, isn't it? So my total displacement is x plus E sine omega t. So if I do that differentiation, what I get is that Fv is equal to mx double dot minus me omega squared sine omega t. So I'm going to substitute for FV now in this first expression. So if we want to make that clear, what we can do is we can just give these three equations little labels, 1, 2, and 3. So I'm going to substitute 3 into 1 to eliminate FV. So if I do that, what happens is I get mx double dot plus cx dot plus kx equals m e omega squared sine omega t. Okay, so this is on the left here, this is small m, okay? So now you can see why we define the overall mass as m minus big M, because it gives us a neater derivation now, because when I make this substitution, the big M x double dot cancels out with the minus M x double dot, okay, so that I end up with this slightly nicer version of my equation. Now we've got this equation, we just do exactly the same thing as we've done in all the previous cases. We assume the harmonic response. Okay, so I'm not going to go through every single step. What I'm going to do is I'm just going to show you what the final xp, remember the particular solutions we did last time? Okay, because this left-hand side is exactly the same as what we've done in all the previous cases. The only thing that's different now is that the right-hand side is slightly different of a forcing case, isn't it? Okay, so as I described in the last lecture, what we're really interested in then is the the particular solution, which relates to the steady-state behavior after all the transient stuff has died down. So in that case, what we get is we get m e omega squared over k, 1 over square root of 1 minus r squared, all squared, plus 2 zeta r squared, and then this is times by sine omega t minus phi. And hopefully this is really easy to work out compared to what we did last time, because all we've done, if you look, the only difference is that last time we had cos instead of sine. So now in the solution we have sine instead of cos. Okay, so that's a direct link. Last time instead of m e omega squared we had f, didn't we? And in the solution we had f over k. Now we've got, instead of that f, we've got m e omega squared over k. So you can just look at the previous example and see that this is a direct substitution. But we can put in brackets from lecture 6. Okay, just as a sort of reminder of where this comes from. And we note that r squared, the frequency ratio, of course, is omega squared over omega n squared, isn't it? Which is equal to omega squared m over k. So omega squared over k is equal to r squared over m. So what we can do is we can replace, in this expression we can take omega squared over k out and replace it with r squared over m. So we get this. Okay, so this is quite nice now, because now we have the mass ratio, the eccentricity of the arm of the unbalanced mass. Here we've got r squared over our familiar square root term, and it's all times by the sine. Okay, so what does it look like? Well, let's draw our normal diagram. So frequency ratio R. What we need to draw here is the dynamic magnification okay, which is r squared over square root of 1 minus r squared plus 2 zeta r all squared. So if we put on there the point 1, okay, so what we see is that this function, because it's got r squared on the top of it, when r is 0, the whole thing's 0. Okay, so that's a bit different from what we've seen before. And in fact, what this function looks like is it starts at 0, it goes up, and then it goes and starts to become asymptotic towards 1 as it gets larger and larger. So this is a little bit similar to the inertance function that we looked at last time. If you remember the frequency response function where we had acceleration divided by mass, looks a little bit like this, in the sense that it went asymptotic towards 0 on this side, and it went to 1 over m on the other side. Okay, so what's interesting is that you have to be cautious, because it's easy to get this mixed up with that that type of FRF. Okay, it's also easy then to identify if you haven't got an inertance, if you've got a displacement-based problem. Okay, if you see a picture like this, it's almost the opposite to the normal forcing case, isn't it? Okay, the normal forcing case looks like that. Okay. So then the forcing case we did last week looks like that, where it starts at 1, okay, and does something like this. So this one is almost, it's like it being flipped the other way. Okay, so just by looking at, sometimes you're shown a picture in an exam or in a question, and you're asked to do something. So the first thing to work out in your mind is, which way round is this dynamic magnification factor? And as a result, is it a standard forcing case, or is it something like a rotating mass forcing case? Okay? Right.